All right, here we go. Chapter 9, problem set number 2. First one is problem number 13. Problem number 13 says that a shell is shot with an initial velocity of 20 meters per second and an angle of 60 degrees with the horizontal. At the top of its trajectory, the shell explodes into 2 fragments of equal mass. One fragment whose speed immediately after the explosion falls vertically. How far from the gun does the other fragment land, assuming that the terrain is level and air drag is negligible? So let's put up what we got here. So our initial velocity is 20 meters per second. And only goes 60 degrees. Okay, so a standard projectile problem to start. So let's break it up into its horizontal and vertical pieces. So this is the V in the X direction. This is the V in the Y direction. This is 20 meters per second. So if I want to get, sorry, there's some construction going on next door. V in the X direction is equal to the V0, 20 times the cosine of 60. Vx is equal to 10 meters per second. And V0y is equal to 20 times the sine of my angle. So here's our initial condition. So how do I find out how much time it's going to take? So we're going to find out how much time it takes just to get to here. And then we can know that if you have this much time to here, you still have the same amount of time down. Because the mass of the projectile doesn't matter. It's still going to fly the same. So if I can figure out how much time to here, I can double the time to get to there. So let's do that. So one of the things we know is in the vertical direction, the velocity is 0 up there. So if I use this, V in the y direction is equal to gt plus v0 in the y direction. So it's 0 at the top, I got negative 10t plus my v0 in the y direction is 17.3. So t is equal to 1.73 seconds. So I know it's going to take 1.73 seconds to get to here and another 1.73 seconds to get back down. If I want to find out how far I went horizontally, I know that the v in the x direction is equal to, so speed is equal to the distance divided by the time. So delta x is equal to vxt. So this is this delta x right here. Delta x is, or Vx is 10, time is 1.73 seconds. So it went 17.3 meters when it gets there. Now, what happens after that? Well, at this moment in time, the shell explodes. But the nice thing about an explosion is all the forces are inside the system. So if it was internal, that means that the momentum is conserved. So at that moment in time, because it happened at the very highest point of its trajectory, it was only moving horizontally. Therefore, the momentum before has to equal the momentum after. So initial momentum equals final momentum. If I take the shell as m moving at speed vx, afterward we're going to have two pieces, one of which is m over 2 moving at some new speed v, plus the other one m over 2, but it fell straight down, so its momentum in the x direction was 0. And so if I go to solve for this, these m's magically disappear. And what that tells me is that the new velocity, my velocity of my new shell, is equal to 2 times the velocity of the shell that was there. So before it was moving at 10 meters per second, now it's going to be moving at 20. So it doubled its speed. So it lost half the mass and doubled its speed. And now we can see how far this new piece went. We know that delta x is equal to vt. The new velocity is 20 meters per second. And here's the thing. Again, on its path, the mass doesn't affect the time in the air. So it was 1.73 to get to the top and 1.73 seconds to get back down to the bottom. So that's got to be 34.6 meters. And the question asks, what's the total distance? So the total distance would be the first half of the trip plus the second half what's that, 51.9? Look at problem 21. Actually, problem 21 is pretty complicated, so let's start reading what it says. So 21 says that a 0.3 kilogram softball, that's going to be important later. .3 kilogram softball has a velocity of 15 meters per second at an angle of 35 degrees below the horizontal. So this is the 15 meters per second at an angle of 35 degrees below the horizontal. Just before making contact with the bat. What is the magnitude of the change in momentum of the ball while in contact with the bat if it leaves with a velocity of 20 meters per second vertically downward? So this is the initial condition. What if it leaves this way? Okay, so the new velocity is 20 meters per second directly downward. We want to find the change in momentum. Well, here's the deal. When we talk about the change in momentum, the change in momentum is the final momentum minus the initial momentum. That's how you calculate it. But don't forget that all three of these things are vector quantities. So we're going to have to add them like vectors. So let's find out what the initial momentum is here. To get the momentum of this guy here, I'm going to draw it. Okay. It's 15 meters per second, but that's the speed. In order to get the momentum, you got to do mv. So 15 meters per second times 0.3. So the momentum, the initial momentum is actually 4.5. So we're going to do final minus initial. So here's the final, okay? So when I go to draw the final here, let me get a better place for it. So here's the final momentum. So this is PF, and it's equal to 20 meters per second times 0.3. 20 times 0.3 has got to be 6. So this is 6 is the final momentum. Now, what I need to do is I need to add negative initial momentum to it. So this is the initial momentum direction, so I'm going to add the opposite to it. Now think about this. This is to the left and up. So this is 15 times 0.3, so this is 4.5. So that's the negative, it's the opposite of the initial. And what that means is that if we're going to get the change then, we do final plus negative initial. And this makes sense to us because it was moving to the right and down, now it's only moving down, so this change in momentum was to the left and down. So that seems okay to me. So how are we going to figure this out? Well, one easy way to do it is to just make it into a rectangle. If we make it into a rectangle, we can probably get all of these pieces. So this is 35 here. Okay, so we're going to use a little bit of trigonometry to figure out what those sides are. So hypotenuse is 4.5. So this is 3.69 for that side. And this is 2.58 for this side. So this is total 6 up and down. This is 2.58 here. So this length here is 3.42. And this is 3.69 and this is 3.69. It's a rectangle. So if I want to calculate the length of this vector, which is the change in momentum vector, I'm going to use the Pythagorean theorem. So according to this, the change in momentum will be equal to 3.42 squared plus 3.69 squared. Oh, don't forget to square it. And I get the change in momentum is equal to 5.0, and that's kilograms meters per second. Oh, I should have done that over here. Sorry, I'm going to need to draw over here. So what happens if it gets shot right back out horizontally this time? So we're going to use the exact same understanding here, where this time we're going to take our final momentum, and again we're going to subtract off our initial momentum. So here's the final momentum this time. Okay. Again, it's 20 meters per second. So the final momentum is equal to 6. And this time we're going to, again, all right, we're going to subtract off the initial, which is this one right here. So when you draw that, let me get rid of this thing here, put it on the bottom. So again, this is the same, so it's to the right and up. 3.69, 2.58. Let's make a rectangle again. So the up is 2.58, because it matches that. The horizontal this time is 3.69 and 6, so this is 6, nope, 9. 9.69. So to get the actual change in momentum here, let's use the Pythagorean theorem again. 9.69 squared plus 2.58 squared. Put in your handy dandy calculator, and change in momentum is equal to 10 kilograms meters per second. And if you notice the lengths, this one is supposed to be 5 and this one is supposed to be 10, and within my ability to draw, I think that looks pretty good. All right, that's about a 25. 25 nice and easy. 25 nice and easy. 25 says a 1.2 kilogram ball, let's write that down. .25 kilogram ball, hitting with a speed of 25 meters per second, so its initial speed is 25 meters per second, rebounds with a speed of 10 meters per second. What impulse acts on the ball during the contact? All right, so when we talk about impulse, they are referring to in this textbook as the change in momentum. Now, what we saw in the class is the change in momentum. You can calculate it if you know the m delta v, but you can also calculate it and set it equal to the f delta t. Now, if we're using f delta t, then what we're referring to here is the average net force. So here's our understanding here. So this one, we're not given any forces, so we're just going to use m delta v. So I'm going to go to get the impulse. Now, to confuse you, they use a capital J for impulse. And we're going to do m delta v here. Mass is 1.25. Now, here's the tricky part. To do the change in velocity, you're going to do final velocity minus initial velocity. You're going to be tempted to do 10 minus 25, final minus initial, but it doesn't say initial speed, it says initial velocity. So when I think about that, I have 1.25. If I go to put the velocities in, this one is down. So this is actually, its initial velocity is negative 25. So I'm going to do 10 minus negative 25. Oh, it's 1.2, that's wrong, sorry. Mass on 1.2 kilograms. So that is the impulse that acts on the ball. Now, if the ball is in contact with the floor for 0.02 seconds, what's the magnitude of the average force from the floor on the ball? Okay. So, if I look at this here, the impulse is also equal to the F delta T. If the impulse is 42, the force from the floor, and this is 0.02, we can calculate the force directly. Force is equal to 2,100 newtons. Here's a weird one. After a cable snaps and the safety system fails, an elevator cab free falls from a height of 36 meters. During the collision at the bottom of the elevator shaft, a 90-kilogram passenger is stopped in 5 milliseconds. Assuming that neither the passenger or the car rebounds, what are the magnitudes of the impulse and the average force during the collision? Well, what we're saying here is that during this collision, okay, well, we got to do a couple things. We got to figure out how far it's gone, but during the collision, okay, all right, the elevator is going to come to a stop, which means the person on the inside is going to come to a stop. This happens in 0.05 seconds, and right before it hit, it was moving, and then it comes to a stop. So let's figure out how fast it was moving. So there's a lot of different ways you can do this. Okay, you can use an energy concept, you can use a kinematics concept. I'll do it this way. I know that for an object that's falling, I know that v squared is equal to v0 squared plus 2g delta y. This is for a falling object. I'm going to solve for the final velocity. It was released from rest plus 2 times -10 times -36. So this is the velocity right before it hits the ground. Okay, this is the velocity right before it hits the ground. And that's 26.8 meters per second. So during the collision, the VI is actually equal to 26.8 meters per second. The VF is equal to 0. We know the mass is 90. So we can calculate the impulse. If the impulse is equal to mass times the change in velocity, 90 times final minus initial. Actually, what's interesting is you had to take the square root here, but it's moving downwards, so this will actually be negative. It's going to be negative also. 0 minus a negative 26.8. Now again, if you are using a G value of 9.8 or significant digits, your numbers are going to vary a little bit. But we're trying to get in the ballpark. So this is the actual change of momentum. Now, because this is a vector, this is also a vector. And the velocity ends up being, it's slowed to a stop. So this is in the up direction, that's why it's positive. So negative because the initial velocity was down, and this change of momentum is up. If I want to find the force, the average force, all right, I know my momentum is 2412, and the time is 5 milliseconds, 0.005 seconds. So I got 482,400 newtons. It's a lot of newtons. It's a lot of newtons. Now, in the second half of the problem, they said, well, what if you jumped, right? What if you jumped? And they give the jumper, this guy can jump with a velocity, a relative velocity of 7 meters per second. Which means that right before he hits the ground, he's going to try to jump. So he's going to jump upward relative to the elevator. I don't know how he does that, but 7. So we're actually going to do the same thing here, and we're going to calculate the new impulse and the new force. The only thing that's going to be different is instead of the initial velocity here being 26.8 or negative 26.8, the initial velocity is going to be negative 19.8 meters per second. I think this problem highlights the absurdity of the idea that if you think about this in terms of miles per hour, if you fell from 36 feet, which is about a 3-floor fall, so falling from the 4th floor down to the ground, to get to miles per hour, you got to multiply by about 2.2. So we're talking maybe 60, 65 miles per hour that you'd be moving right before you hit the ground. And so you could never jump with that speed. So I think it's highlighting the absurdity. So just do the same thing. Mass is still 90. This time the change in velocity is 19.8. And then if you want to calculate the force, we still see that it's thousands. Of newtons. Weirdly enough, we have another softball problem. Since it's figure 9.5 shows a 0.3 kilogram baseball. Oh, this one's a baseball, sorry. Baseball. .3 kilogram baseball, just before and just after it collides with a bat. Just before, the ball has a velocity of v1, 12 meters per second. At an angle of 35 degrees. Okay, you'll notice the angles there. Just after, it's traveling directly upward, you'll notice that there, with a speed of 10 meters per second. And this all happens in a time of 2 milliseconds, so 0.002 seconds. What are the magnitude directions relative to the positive direction of the x-axis of the impulse on the ball from the bat? Okay, so we're going to use the same idea we did last time, where our understanding is that the impulse we're going to calculate as the change in the momentum. Again, a vector. And we're going to take the final vector, final momentum vector, and we'll subtract off the initial momentum vector. So this time it's going to be momentum 2 minus momentum 1. So let me see if I can't draw that. So 2 minus 1, which is plus and negative 1. So I want this to be the final momentum. That goes with this velocity, but it's a momentum. And then this one. This is our negative initial momentum vector. So the initial momentum vector would be this way. This is the negative one is this way. And so if I then go to draw the change in momentum vector, it's final plus negative initial. You draw from the open tail to the open tip. And this is going to be the change in momentum vector. So we're going to attack this the way we did this the last one. We know that this negative pi is up and to the right. So if we can get some values for these, I think we can make a go at it. Remember, the whole concept here is that the momentum is equal to the mass times the velocity. So we have the speeds here, but we need the momentums. So this is PF. According to our diagram, V2 is 10, but this is 0.3, so this was equal to, the final momentum was 3. This was 12 times 0.3, which was 3.6. I know the angle here is 35 degrees. So I'm going to use some trigonometry to make these happen. Hypotenuse is 3.6, angle is 35. So this one here is 2.06. Is 2.95. And so if I want to get this momentum, final momentum vector, I'm going to make it into a rectangle. And figure out what the sides are, and then use Pythagorean theorem. The horizontal here is 2.95, because it's a rectangle. The vertical, I have 2.06 and 3, so 5.06. So to get the change in momentum, I'm going to take 5.06 squared plus 2.95 squared. So I have 5.86 kilograms meters per second. And if I want to get the angle relative to the x-axis here, if I want to get that theta, I'm going to use tangent. So tan theta would be equal to the ratio of the opposite side to the adjacent. Ooh, got a little excited. Theta is the inverse tangent. So theta is equal to 59.8 degrees. And that actually looks pretty good, right? Definitely bigger than 45. I feel okay about that. So this is the magnitude and angle of the change in momentum. The next question says, C says, what are the magnitude and direction of the average force on the ball from the bat? Well, we can use our same idea here, that the impulse, the change in the momentum, is equal to F delta t. So this is how we're going to get the magnitude here. So the number, the change is 5.86 force times, it says the time is 2 milliseconds. Okay, so the force is equal to So that is the magnitude, and what I like about this is if you look at the equation, you'll notice that time is a scalar, so the force vector and the change in momentum vector have to be in the same direction. So the angle is 59.8 degrees from the x-axis. $35. The figure shows an approximate plot of force versus time during a collision of a 58-gram super ball with a wall. All right, so we got a super ball here. The mass is 58 grams. Now we have to work in kilograms. So there's 1,000, so I'm going to divide. So 0.058 kilograms, that's the mass. Now this ball rebounds off the wall. It hits with an initial velocity of 34 meters per second and rebounds directly back with approximately the same speed. So if we diagram that up here, okay, so here's our wall. Okay, the ball's coming in, comes in, hits, and leaves with the same speed. Now, here's what they mean by the same speed. We know that this value is 34 meters per second coming in and 34 meters per second coming out. So how do you figure out the change in velocity? Well, remember, it's velocity, not speed. So this one's moving left, so its velocity is negative. This one's moving right. Its velocity is positive. So if you want to calculate, all right, it says, it just skips to the chase, it says, what is the F max? So it wants to know this value right here. It wants to know what the F max is. Well, here's how we're going to do it. We're going to use our impulse concept again. So impulse. We know you can calculate it if you know m delta v. And we know m and delta v down here. We're going to get that. Remember, it's also equal to the area of an F versus T graph. That was a whole lab that we did where we measured that area. And so we can get the area, we can get, if we can find the impulse, then we can use it to set these two things equal to each other. So let's get the J down here first. So if I go to calculate the impulse down here, mass times the change in velocity, which is mass times V final minus V initial. So 0.058 times 34 minus, the initial was negative 34. Plug it in the calculator. So I got 3.944 is my impulse. And now what I'm going to do is I'm going to set it equal to this area up here. But let's look at the area. I'm going to break the area up into three sections. I'm going to break it up into this triangle, this rectangle, and this triangle here. So I'm going to calculate the area. It's going to be area of triangle 1 plus the area of the rectangle plus the area of triangle 2. One thing to note is that this is the time in milliseconds, not seconds. That's going to be important later when I actually go to calculate the area. So this is 1/2 the base. Now, it's 2 milliseconds. So I'm going to do it in milliseconds first and we'll come back. So 1/2 of 2 times F max. 1/2 the base times the height. Plus, let's do the rectangle. It's base times height, so 2 times F max. Plus, I have another 1/2 base times height. So we're going to calculate that. 1/2 of 2 is 1, so I have 1 F max, 2 more, and then 1. So there's a total of 4 F max. And the 4 is the time component here, but it's really for milliseconds. So when I go to calculate that, it's really 0.004 times f max. And I know that this is my impulse here, and this is my impulse here. I'm going to set them equal to each other. And I end up with 986 newtons is my F max. And that's it.